assemblies to drive the fly-by-wire rudder control system. A pair of cockpit control transducers, CCTs, are connected to each rudder pedal assembly, providing the electrical signals to the primary ACE modules, effectively replacing the control cables of a conventional aircraft. Two independent primary ACE modules drive the upper and lower PCU, providing the analog rudder control functions implemented in the primary ACE hardware, such as gain shaping to vary the pedal-to-surface gearing as a function of the magnitude of the pilot input. 4 independent FCM units, located in MAU 1 and 3, provide high-level system augmentation to the primary ACE units, such as yaw damping, turn coordination, as well as gain scheduling as a function of airspeed. The flight deck controls include 2 pedal assemblies, which rotate a pair of forward torque tubes located under the flight deck. Each pedal assembly incorporates 2 rudder pedals mounted on arms, rotating forward and backward. Rudder pedal travel is limited by system stops, located on each forward torque tube. A push rod attached to each pedal provides the input force to a Y-arm, which in turn drives the interconnect linkage connecting the 2 pedal assemblies. The Y-arm also provides input to the 2 cockpit control transducers per side. A feel unit, located between the 2 torque tubes, provides the feel and centering force to both rudder pedal assemblies. It is grounded to the aircraft structure by the trim actuator. For airplanes certified to perform Cat 3 operation, 1 optional autopilot servo is attached to the forward torque tube assembly. The dual artificial feel unit provides an artificial force to the rudder pedals, which increases in linear fashion as a function of control pedal displacement. The artificial feel unit consists of 2 cartridges with preloaded springs, extending and retracting according to the pedal commands, providing an independent force feedback to the left and right pedal assemblies. The artificial feel unit is grounded to the aircraft structure through the trim actuator. The preload in the unit is sufficient to overcome friction within the pedal assemblies, thus returning the pedals to the neutral position with no pilot control input. With 1 cartridge disconnected, the feel loads on both pedals are reduced to 1/2 of the total force. An additional actuator trim disconnect cartridge provides backup feel force in case the AFU grounding through the trim actuator is disconnected. The cockpit command transducers sense the pilot rudder pedal inputs by converting the mechanical deflection of the rudder pedal assembly into electrical signals that are transmitted to the primary ACE units. There are 4 single linear variable differential transformers, or LVDTs, installed. 2 attached to the pilot's torque tube, and 2 attached to the co-pilot's torque tube. A shear-out mechanism protects the rudder pedals from jamming in the unlikely event of a jammed LVDT. Each LVDT interfaces directly with the primary ACE unit, controlling the actuator of the same side, resulting in the pilot controlling the upper PCU and the co-pilot controlling the lower PCU. This distribution ensures additional redundancy between the left and right side rudder systems. 2 electro-hydraulic actuators, or PCUs, drive the rudder control surface. The PCUs are attached directly to the rear spar of the vertical stabilizer. They are controlled by the associated primary ACE, commanding the PCU to drive the rudder surface via the toggle links. The 2 PCUs connected to the rudder surface operate in an active standby mode, resulting in one actuator being energized and actively controlling the surface, while the standby PCU acts as a hydraulic damper, providing flutter protection. The active standby status of the PCUs is alternated by the primary ACE units at the power-up on ground each day, or automatically switched when a failure is detected. The upper PCU is powered by Hydraulic System 1, while the lower PCU is powered by Hydraulic System 3. The rudder control system uses electro-hydraulic actuators to drive the rudder control surface, controlled by the associated ACE channel via an electro-hydraulic servo valve. Each actuator assembly is a hydraulic cylinder with a steel piston in a steel cylinder. An inlet check valve located in line with the pressure port has a flat lapped poppet and a sharp edge on the seat, which allows the valve to shear through contamination. The PCU includes a solenoid-activated pressure reducer, which is normally open when energized, will send the supply pressure of 3000 psi directly to the pressure transducer and through the inlet check valve to the mode select solenoid valve and to the EHSV pressure port. With the PCU in the active mode, the mode select solenoid valve is open, energized, to pilot the mode select valve to the active position. In the active mode position, the EHSV controls the main ram. The primary ACE receives several electrical feedback signals from the LVDTs housed in the PCU and the LVDTs mounted to the rudder surface, ensuring a closed-loop control, as well as permanent monitoring of the PCU for failure detection. An LVDT on the main ram transmits actuator piston position information to the primary ACE, used in conjunction with the inputs from the surface position transducer to determine actual rudder position. Another LVDT mounted to the electro-hydraulic servo valve returns actual position of the valve, and a pressure LVDT detects hydraulic pressure loss within the actuator. The two surface position transducers also provide data to other aircraft systems, such as the ICUS and the flight data recorder. The trim system allows the pilot to offload any unwanted force from the rudder pedals. This is accomplished by adjusting the neutral field position of the pedal assembly. The rudder trim system consists of an electromechanical linear actuator attached to the artificial field unit, AFU, and grounded to the aircraft structure and the trim control panel, TCP, located on the center pedestal in the cockpit. The system is operated by a rotary yaw trim control switch on the TCP, commanding the actuator to move, repositioning the ground point of the artificial field unit, which in turn repositions the neutral position of the rudder field system. The actuator is equipped with a timer, limiting a single trim command to 3 seconds. A quick disconnect switch, located on the pilot and co-pilot control yoke, disables the trim actuator by removing DC power to the trim motor. A potentiometer within the actuator provides position indication to the ICUS. During normal operation, either pilot can push on their left or right pedal to achieve the desired yaw of the aircraft. The push rods attached to the pedals then transfer the force applied into torque rotation of the torque tube assemblies. The first 14 pounds applied is required to break out the field mechanism, and the field force is provided back to the pilot. With rotation of both torque tubes, all 4 command LVDTs provide equivalent pedal position to the primary ACEs. The active primary ACE then compares the position of the LVDT in the main ram of the corresponding PCU to the commanded position from the LVDTs. The error between command and surface position is converted to an electrical signal to the EHSV, which commands the PCU to eliminate the error. The other PCU that is in standby mode remains in bypass through the damping orifice that allows the PCU to be back-driven by the active PCU and provides flutter protection. For Cat 2 operations, there are no mechanical rudder inputs from the Autopilot. The AFCS provides yaw damper and turn coordination signals directly to the FCM over the avionics standard communication bus. The FCM modules then transmit the commands to the rudder primary ACE modules via CAN bus interface. The commands are summed in series with the normal pilot commands before being modified by the rudder gain schedule. The Autopilot authority is limited electronically. The limits are provided by the torque limits in the AFCS. For Cat 3 operations, a single Autopilot servo is installed at the forward torque tube. The thrust asymmetry compensation function applies computed rudder input signals to the primary ACE in order to reduce the yawing moment produced by asymmetric engine thrust. The TAC function is computed in the FCM as a function of N1, Mach, pressure altitude, and temperature. During takeoff, TAC is enabled 10 seconds after liftoff, reducing the maximum pilot pedal authority from 30 degrees to 18 degrees. In the event of engine failure, the TAC function then provides up to 12 degrees of rudder input to help compensate for the resulting yaw moment, while the pilot provides the rest of the required rudder input via the rudder pedals. In case of a failure of one or more sensors required to perform the TAC function, a TAC fail advisory message will be displayed on the upper right portion of the ICUS display, and thrust asymmetry compensation will not be available. The primary ACE unit incorporates a function to limit the rudder authority in the event the rudder control system is forced into direct mode, with no more airspeed gain scheduling available. Structural protection for the vertical fin and the empennage is then provided via hinge moment limiting of the rudder surface. The hinge moment limiter reduces the available hydraulic supply pressure to the actuator from 3,000 psi to a maximum of 930 psi by engaging the pressure reducer installed in each PCU. In this case, the maximum rudder authority is available at low speeds for flying the approach, but will be reduced for increasing airspeeds due to surface blowdown. The rudder will still provide enough authority for single-engine control at any airspeed. The rudder control system can be forced manually into direct mode by using the mode select switch on the FCP, located on the center pedestal in the cockpit. A loss of the hydraulic supply or a PCU failure, such as an actuator runaway or a mechanical disconnect, will be detected by the primary ACE and the failed PCU will be shut down. Control of the surface will automatically be switched to the other PCU. In the event of a jam in either pilot's rudder pedal assemblies or in one of the rudder PCUs, the rudder will remain fixed at the position where the jam occurred. The pilot will have sufficient control of the aircraft using the ailerons and the roll spoilers. If a trim runaway occurs, the rudder pedal neutral point will shift, requiring the pilot to exert a constant force on the rudder pedals to maintain neutral directional control. Control authority will be normal, but control forces will be asymmetrical. If the trim actuator disconnects from the system, the backup centering spring of the feel mechanism will provide feel and centering. The following rudder system messages may be displayed on the ICUS. Caution message, flight control no dispatch, is displayed when one of the components associated with the flight control system has failed to no-go condition. The caution message, rudder fault, indicates that the rudder control system has reverted to direct mode. The caution message, rudder fail, illuminates when active and standby rudder channels have failed or rudder has jammed. The caution message, rudder limiter fail, is displayed when rudder ground authority has been retained after takeoff. Caution message, flight control fault, is displayed if one of the components associated with the flight control system has failed. Advisory message, YD fail, will be shown if yaw damper function is failed. The elevator control system uses conventional control column assemblies to drive the fly-by-wire elevator control system. A pair of cockpit command transducers connected to each of the two independent torque tube assemblies provide the electrical signals to the primary ACE modules, effectively replacing the control cables of a conventional aircraft. A total of 4 primary ACE channels are used to independently control each of the 4 PCUs, providing the analog elevator control functions implemented in the primary ACE units, such as gain shaping, to vary the control column to surface gearing as a function of the pilot's input command. 4 independent FCM units located in MAU 1 and 3 provide high-level system augmentation to the primary ACE units, such as gain scheduling as a function of airspeed, elevator thrust compensation, angle of attack limiting, Mach trim, and configuration trim. The flight deck controls include 2 column assemblies used to command a pair of forward torque tubes located under the flight deck. Each control column drives its onside torque tube assembly through a push rod attached to the base of the control column. Mechanical system stops located on each forward torque tube limit control column travel to 7 degrees nose down and 10 degrees nose up, resulting in a maximum elevator surface deflection of 18 degrees and 25 degrees respectively. The control columns are mechanically linked through the torque tube assemblies by a disconnect device. 2 LVDTs are attached to each torque tube, converting its motion into electrical signals. 2 independent feel units, located at the outer edge of each torque tube, provide feel and centering force to both control columns. Autopilot input to the elevator system is carried out by 2 autopilot servos attached to each torque tube assembly, replacing manual control column inputs by the pilots. A 28-volt DC stick shaker motor is attached to each control column, creating a vibration that warns the pilot when approaching stall conditions. The motor is activated through the stall warning system, provided by the Autoflight Control System, AFCS. The 2 artificial feel units, or AFUs, mounted to the pilot's and co-pilot's torque tube assemblies provide an artificial force to the control column, which increases linearly as a function of control column displacement. Each AFU consists of a preloaded spring, extending and retracting accordingly as the control column is moved forward or backward. One end of the AFU is grounded to the aircraft structure, while the other end is attached to a bell crank on the column torque tube. With no pilot input on the control column, the feel unit returns the system to the neutral feel position. The sum of the 2 units provides the correct feel force to the pilots in regard to control column displacement. In case of a column or feel unit disconnect, the feel force on the control column is reduced to half of the total force. The cockpit command transducers sense the pilot control column inputs by converting the mechanical motion of the control column assembly into electrical signals that are transmitted to the primary ACE units for elevator surface positioning. 4 single linear variable differential transformers are installed. 2 attached to the pilot's torque tube and 2 attached to the co-pilot's torque tube via a bell crank. In the unlikely event of a jammed LVDT, a shear-out mechanism on the bell crank protects the control columns from jamming. Each LVDT interfaces directly with the 2 primary ACE units, controlling the elevator PCUs of the same side, so that the pilot controls the 2 actuators driving the left elevator surface, and the co-pilot controls the 2 actuators driving the right elevator surface. The elevator control system uses 4 electrohydraulic actuators to drive the left and right elevator control surfaces. The PCUs are mounted to the rear spar of the horizontal stabilizer, 2 on each side. They are controlled by the associated primary ACE, commanding the PCU to drive the elevator surface via the toggle links. The PCU pairs connected to each elevator surface operate in an active standby mode, resulting in one actuator being energized and actively controlling the surface, while the standby PCU acts as a hydraulic damper, also providing flutter protection. The active standby status of the PCUs is alternated by the primary ACE units following a power-up on ground each day, or switched automatically when a failure is detected. The inboard PCUs on each elevator surface are powered by Hydraulic System 2. The left outboard elevator PCU is powered by Hydraulic System 1. And the right outboard elevator PCU is powered by Hydraulic System 3. The elevator control system uses electrohydraulic actuators to drive the elevator control surface, controlled by the associated ACE channel via electrohydraulic servo valve. Each elevator PCU is a hydraulic cylinder with a steel piston housed in a steel cylinder. Hydraulic oil enters the PCU through the inlet check valve, which is located in line with the pressure port downstream of the supply filter. The solenoid valve is an electromagnetic valve that ports fluid to the mode select valve when energized. A spring acts against hydraulic pressure to close the inlet port when the solenoid is de-energized. The mode select valve is a 4-way valve, which is active when pressurized and in bypass damping mode when depressurized. The EHSV is a deflector jet valve. The servo valve operates on a DC control voltage and is fully open in the extend or retract position. The EHSV will receive inputs from the primary ACE to select retraction or extension off the actuator. A return relief valve is provided to ensure that a quantity of fluid is retained in the PCU for damping after the loss of hydraulic system. One electrical connector will receive inputs from the pressure transducer and from the compensator piston, and a second one will receive EHSV and piston LVDT signal and forward these values to the primary ACE. During normal operation, either pilot pushes or pulls the control column to achieve the desired pitch of the aircraft. The push rods attached to the columns then transfer the force applied into torque rotation of the torque tube assemblies. The first 2 pounds is required to break out the feel mechanism, and the feel force is provided back to the pilot. With rotation on both torque tubes, all 4 commanded LVDTs provide equivalent column position to the primary ACEs. The active primary ACEs then compare the position of the LVDT in the main RAM of the corresponding PCU to the commanded position from the command LVDTs. The error between command and surface position is converted to an electrical signal to the EHSV, which commands the PCU to eliminate the error. The other PCUs that are in standby mode remain in bypass through the damping orifice that allows the standby PCUs to be backdriven by the active PCUs and provide flutter suppression. Engaging the autopilot on the automatic flight control system guidance panel, which is located in the cockpit, causes the autopilot to take over the pilot input commands to the elevator control system. Two autopilot servos connected to the pilot torque tube via cables provide AFCS inputs to the elevator control system. During autoflight, the autopilot servos respond to commands from the AFCS and move the pilot's torque tube, the co-pilot's torque tube, and the control columns. Control of both elevators via the cockpit LVDTs, primary ACE, and FCM units, and the elevator PCUs remains the same. Autopilot pitch trim commands are generated within the AFCS and sent to the FCM modules, where they are summed with the configuration trim commands computed in the FCM. Trimming is then accomplished by moving the horizontal stabilizer. The primary ACE receives several electrical feedback signals from LVDTs and pressure sensors housed in the PCU and mounted to the elevator surface, ensuring closed-loop control and permanent monitoring of the PCU for failure detection. An LVDT on the main RAM transmits actuator piston position information to the primary ACE and is used along with the inputs from the surface position transducers to determine actual elevator surface position. Another LVDT mounted to the electro-hydraulic servo valve returns actual position of the valve, and a pressure sensor detects hydraulic pressure loss within the actuator. The surface position transducers, 2 per elevator, also provide data to other aircraft systems, such as the MFD synoptic page and the flight data recorder. With the elevator control system operating in normal mode, the elevator is gain scheduled as a function of airspeed, reducing elevator movement with increasing airspeeds. The FCM adds additional high-level functions to the pilot inputs, such as elevator thrust compensation and angle of attack limiting. In the event of loss of airspeed information, the FCM is reduced from the control loop, and the associated primary ACE reverts into direct mode, using a maximum low-speed gain for the elevator to ensure aircraft controllability during approach and landing flare. FCM functions like elevator thrust compensation and angle of attack limiting are then no longer available. The elevator control system can be forced into direct mode by using the mode select switch on the FCP, located on the center pedestal in the cockpit. The elevator thrust compensation function, ETC, helps to reduce the pilot workload by applying elevator inputs to reduce the pitching moment produced by increasing or decreasing engine thrust. The ETC function is computed in the FCM as a function of N1, Mach and pressure altitude. Elevator input is limited to plus or minus 5 degrees and is applied proportional to the amount of engine thrust above or below the reference thrust setting. The command is sent to the primary ACE units via the CAN bus interface and is then summed with the normal pilot input. If one or more sensors required to perform the ETC function fail, the function is no longer available, and the respective message will be displayed on the ICUS. Stall warning is provided by the Auto Flight Control System, AFCS, by activating the stick shaker motor on the control column. Stall identification is provided by the FCM by means of the angle of attack limiting function. Once the stick shaker is activated by the AFCS, the angle of attack limiting function reduces control column authority in the nose-up direction gradually until the control column reaches the aft stop, thereby limiting the angle of attack. The FCM computes an angle of attack limiting command using angle of attack data, control column position, and inertial feedback. The command is sent to the primary ACE units, where it is added to the normal pilot input. If one or more sensors required to perform the angle of attack limiting function fails, the function is no longer available, and the respective message will be displayed on the ICUS. A loss of the hydraulic supply to either one of the PCUs is immediately detected by the pressure sensor in the PCU, and control is automatically switched to the other PCU. A PCU failure, such as a PCU runaway or a mechanical disconnect from the wing structure or the surface, will be detected by the primary ACE, resulting in the shutdown of the failed PCU. Control of the surface will be automatically transferred to the other PCU. If a jam in one of the elevator PCUs is detected, the respective elevator surface will remain fixed at the position where the jam occurred. The pilot will be able to control the aircraft using the remaining elevator. The following ICUS messages will be displayed in the cockpit. Warning message, elevator normal mode fail, indicates that the normal mode of the elevator system is no longer operative. Caution message, flight control no dispatch, indicates one of the components associated with the flight control system has failed to a no-go condition. Caution message, elevator fault, displayed when left and right elevator system has reverted to direct mode. Caution message, elevator LH or RH fail, indicates that the remaining elevator will revert to direct mode if both PCUs are disengaged. The remaining elevator will remain in normal mode in case of a surface jamming. Caution message, elevator THR comp fail, shown when one or more sensors required to perform the elevator thrust compensation function have failed and the function is no longer available. Advisory message, pitch control disc, indicates that the control column is disconnected. Advisory message, flight control fault, indicates that one of the components of the flight control system has failed. The Stall Warning and Protection System, SWPS, provides a two-stage system to warn and avoid the Embraer 170 and 190 family aircraft from stall. When the airplane is closer to stall conditions, the SPWS provides a warning to the pilots by shaking the control column. If the stall condition persists, the SPWS prohibits stall by automatically applying a pitch downforce on the control column. The Automatic Flight Control System channels 1 and 2 each hosts a separate stall warning and protection system function. In case of a single SWPS channel being inoperative, the pilot can select the other SWPS channel to provide stall protection by using the cutout buttons on the SPS panel. If both channels are inoperative, or the stall warning protection system in general has failed, the pilot will be notified via ICUS messages. The pilot must then manually operate the airplane to avoid stall using other means of stall detection. The first stage of the stall warning protection system provides a warning to the pilot of the impending stall by activating the stick shaker of each control column, which causes each control column to shake, simulating the aircraft buffeting. In addition, the SWPS provides other warning indications. If the failure is known to the SWPS, the system automatically disengages all operations and enunciates SWPS failure in the display system. However, if the malfunction is not detected by the stall warning protection system, the system may activate the stall warning and protection measures in non-stall conditions. In such abnormal operations, the pilot may attempt to switch the SWPS channel using the SPS panel. If both SWPS exhibit same abnormal conditions, the pilot must ignore the stall warning, shaker, measures, and detect stall characteristics using other means. Displaying low speed awareness, LSA indication on the airspeed tape. Displaying pitch limit indication on the attitude direction indicator, ADI, of the primary flight display, PFD. Providing stall warning enunciations, CAS messages on ICAS. The second stage of the SWPS prohibits stall of the aircraft by activating the angle of attack limiting function. PFD indications are as follows. Pitch limit indicator indicates the margin left to the stick shaker angle of attack set point. Indication is presented whenever the margin reaches 10 degrees. The color is green for margin from 10 up to 5 degrees. Amber for margin between 5 and 2 degrees. Red for margin below 2 degrees. Low airspeed awareness. Displayed in the airspeed scale when the airspeed is near stall speed for the current configuration. The stall protection system panel has the following controls. The cutout button cuts out the associated channel. A striped bar illuminates inside the button to indicate that it is in the cutout position. The horizontal stabilizer control system installation consists of the pilot's and co-pilot's pitch trim switches and the quick disconnect switches, located on each of the two control yokes. A backup pitch trim switch is located on the trim control panel, located on the center pedestal in the cockpit. The trim switches are electrically connected to one HSACE unit, located in the aft avionics bay. The HSACE unit provides control to the electromechanical actuator, referred to as Horizontal Stabilizer Trim Actuator, HSTA. Attached on the upper end to the empennage, and on the lower end to the horizontal stabilizer structure. The FCM units provide additional trim commands to the HSACE via the Control Area Network bus interface. The Horizontal Stabilizer Actuator Control Electronics, HSACE, is a dual-channel active standby system. During normal operation, one channel operates in the active mode, actually controlling the actuator, while the other is in standby. The flight control module alternates the active standby configuration of the channels following the first power-up each day. Channel 1 is powered by main AC bus 1, while Channel 2 is powered by AC Essential bus. Each HSACE channel consists of a control monitor dual-lane structure, providing closed-loop control to one electrical motor on the horizontal stabilizer actuator. The control lane drives the system based on the inputs received, while the monitor lane receives the same inputs and verifies that the control lane is operating correctly. If an error is detected, the monitor lane will stop the electrical motor, in effect shutting down the channel. As a result, the standby channel then becomes the active channel. The Horizontal Stabilizer Trim Actuator, HSTA, is an irreversible single ball screw electromechanical actuator with dual structural load path. The HSA primary load path normally carries 100% of the load from the horizontal stabilizer to the empennage structure. The primary path includes two 28-volt AC brushless motors with integral resolvers. The motors are controlled in velocity by the HSACE and are equipped with manual drive to the motor shaft to check the clutch operation during a maintenance test. Installed between the primary and secondary spur gears, the torque-limiting clutch protects the gearbox and the aircraft structure against high transient loads. The skewed roller torque limiting clutch slips within a preset torque range. The setting of the clutch will be checked at periodic inspection. The third stage spur gear connects the drive to the ball screw of the primary load path. At the ball screw thrust flange, the skewed roller no-back SRNB holds the stabilizer in the last commanded position to prevent the horizontal stabilizer from backdriving under load. The no-back uses rolling friction elements and incorporates two ratchet pawls per ratchet wheel to provide locking. The HSA primary load path connection to the horizontal stabilizer consists of a gimbal attachment from the ball nut to the primary load path structural brackets. The HS actuator also includes two independent resolvers to provide position feedback to the HSACE. One is connected to the primary and the other is connected to the secondary load path. The horizontal stabilizer actuator includes two secondary load paths, the secondary nut load path and the tie rod load path. The two SLPs are normally unloaded, and depending upon the location of the PLP failure, either one or the other becomes loaded. In the event of failure of the ball screw thread or flange, the tie rod will move axially. This motion will engage either of the two splines of the tie rod into the stationary splines of the spherical joint that attach to the structure. The HS attachment failure detection mechanism consists of a split secondary nut and a spring cartridge. The two half shells are normally loose, but still engaged in the ball screw thread. When the split nut becomes loaded, it is free to move relative to its housing. This motion releases the spring cartridge and tightens the two halves of the nut on the ball screw thread. This will cause a jam by excessive friction. At the end of the ball screw, non-jamming mechanical stops limit the actuator stroke in the event that the HSACE fails to stop the horizontal stabilizer at the +2 or -13 degree electrical travel limits. After a primary load path failure, the secondary load path will have a maximum 0.25 degrees of horizontal stabilizer movement. Operation of the secondary load path results in a stalled actuator and a no dispatch message after landing. Manual trim is performed by actuation of the pilot's or co-pilot's dual output split switches, or the dual output backup trim switch located on the TCP. The authority of a cockpit trim switch input is limited to 3 seconds. Thus, the HSACE channel will drive the HSTA motor for a maximum of 3 seconds. Removal of the command resets the timer. When manual trim commands are active and the stabilizer is moving in the correct direction, an aural alert sounds. Each trim switch command has an independent input to both HSACE channels. The HSACE provides closed-loop velocity control of the DC motor in the HSTA by modifying the trim speed of the horizontal stabilizer for any manual switch input as a function of airspeed, which has been received from the flight control module via the control area network bus. Horizontal stabilizer surface speed therefore varies between 0.7 degrees per second for low airspeeds up to 160 knots calculated airspeed and 0.15 degrees per second for airspeeds greater than 250 knots calculated airspeed. Automatic trim input to the HSACE is provided by the flight control module via the CAN bus interface. Autopilot trim functions are provided by the automatic flight control system modules in the MAU and transferred to the FCM via the ASCB bus, while configuration trim is computed within the FCM. Autopilot trim is active when the autopilot is engaged. The configuration trim function commands the horizontal stabilizer as a function of flap setting, spoiler deployment, and auto-throttle offload trim function. All functions are combined within the FCM unit, providing a comprehensive airspeed gain scheduled trim command to the HSACE. The HSACE responds to all trim commands with the following priority: backup trim command, pilot trim command, co-pilot trim command, and FCM trim command. The following trim inhibit commands are implemented in the horizontal stabilizer control system. Pushing the pilot's or co-pilot's quick disconnect switch on the control yoke will disable both HSACE channels, as long as the switches remain depressed, thus disconnecting the autopilot and stopping any active trim command. Releasing the switch will activate the channel again. Two pitch trim cutout switches are located on the trim control panel in the cockpit. Engaging the buttons will disable the respective HSACE channel, forcing it into standby mode by switching off the 28-volt AC control voltage to the channel. The other channel will then become the active channel. In case of stick shaker activation, the HSACE is prevented from responding to any pitch-up trim commands by a stick shaker discrete from the AFCS. In the event of a failure of the horizontal stabilizer trim system, the autopilot cannot be engaged, or if already engaged, will disengage automatically. In the event of a double engine failure causing the ram air turbine to be deployed, the HSACE channel 2 is commanded to emergency power operation mode, leaving the HSTA 2 operational, but at only half the rate. A loss of airspeed data from the flight control module results in low-speed operation of the horizontal stabilizer, providing structural protection to the surface. In the event of a primary load path failure, the load transfers to the secondary load path. Operation of the secondary load path results in a stalled actuator and no dispatch message after landing. Failures within a cockpit trim switch will latch out the failed switch until next power-up, and the respective message will be displayed on the ICUS. The following messages will be displayed on the ICUS in case of system malfunction or as a result of failed built-in test. Caution message pitch trim fail, which indicates both HSACE channels are inoperative and the pitch trim function is no longer available. Advisory message pitch trim SW1 fail, displayed when captain's pitch trim switch is inoperative. Pitch trim SW2 fail indicates that first officer's pitch trim switch is inoperative, and pitch trim backup fail is displayed when backup pitch trim switch is inoperative. Caution message flight control no dispatch indicates after landing that one of the components in the flight control system has failed to no-go condition. The flap system consists of 4 flap panels, inboard and outboard on each wing. Each panel is supported by 2 tracks, with 1 ball screw actuator per track providing the actuation force. All